All right, so welcome back. Today in this video, we are going to be continuing our structural engineering section for the Civil FE exam review. And today we're going to be focusing specifically on elementary statically indeterminate structures. Now, that's a lot of words and they're kind of big words, but we're going to break them down. There's some concepts that you need to know from this section. And so I definitely want to show you where we're at and why I'm saying that this is so important for you as you're studying structural engineering. So currently, this is your FE reference handbook. And so they list out, what's going to be covered. And so we are currently on E, right? So if you missed any of the videos prior that goes through structural engineering, definitely check out those. There's some different concepts, different calculations that you definitely will need to know for this test. All right, so let's go ahead and dive in. Number 1 says, when analyzing a 3-span continuous beam subject to a triangular distributed load, what is a key consideration? Okay, so what information are we given? Well, we're given that it is a triangular load, right? Triangular distributed load. So I'll write out triangular load. What else? And it is a 3-span beam. Okay. So find the most key consideration. All right. So formula is needed. No, none. So you're looking at a 3-span beam, but you're going to need some prior knowledge, right? So anytime they give you like what they're saying, so like in this case they're saying it's a 3-span beam. So what does that mean, right? It means it has 3 different spans. So the first span could be, start off with the fixed reaction, and then it spans, right? And then it's supported by a pin, and then it has a second span, and then supported by a roller, and then it has this third span, right? So each place in between supports are the spans, right? And so the question asks is, what is a key consideration, right? So would it be, and let me draw out what they mean by a triangular load. So it just means that they're putting a force down that is triangularly distributed. That makes sense. So you got force coming down, but it's not all the same. It's in a triangle, basically, coming down along the beam. Okay, so when we're analyzing this, right, and we know that it has a triangular load, what would be a key consideration? Would it be the magnitude of the triangular load? So when you say magnitude, is means the kind of the amount of load. Is that a key consideration? So I would say it's important, but it's not the most important. I'm gonna say no. Beam material properties. Okay. Is this a key consideration? Not really. The support conditions, yes. because let's say you have a beam, if you can support, so what is a support condition? It's whether you have a pin and a roller like we do here and a fixed support, which I'm just drawing my reactions for each of the supports. But if you're you can also have a supports where it could be still a 3-span, right? But you have all rollers, right? And no fixed support, all right? But that's still 3 spans, right? 1 span, 2 spans, and then you got your 3rd span, right? Okay. So no. So you can have different different supports, and that could allow you to be able to hold more or less weight. So that's why this one is going to be more important. Like it's going to be one of the most key considerations, because if you don't know what your supports are, then whether you have a small amount of weight or a really big amount of weight, it's not going to matter, because you don't know how you're going to be able to support it. So once you determine, what type of supports you're going to use, then you'll know, your loading matters. The amount of load that you're taking on matters, but you definitely are going to want to know, how that load is going to be able to go ahead and support all that loading, or it doesn't matter, right? So C is your better answer. Magnitude of the triangular load, though, is important, but the C is the better answer. All right, let's look at number 2. In analyzing a continuous beam with an internal hinge at the center, what is a key consideration? All right, so what information are we given? It's a continuous beam, and there is an internal hinge at the center. Okay. All right, so what is the, we're trying to find the key consideration, right? Okay. So what formulas might we need? Say none. It's another prior knowledge question. All right. So if you have a hinge at the center, right, what does that look like? So you got this beam, and there's a hinge right there. And normally they call this out. Let's say you have a pin and a roller. So here's my hinge. And it's a hinge at the center. So when you're analyzing this, would you need, with the material properties of the beam, be a key consideration? No. I mean, it's something you would need to know, but it's not like the most key thing. Right? So the span lengths of the beam Nope. Yeah, no. The presence of the internal hinge. Say yes. So in analyzing a continuous beam, what is the key consideration? The hinge, right? The hinge. Why is that hinge there? And what does it do, right? So, or the magnitude of the applied load. No. So when you put a hinge here or hinge at the center, it allows basically for the beam to be a lot more flexible as far as loading is concerned. And so that hinge is going to be able to, when you break this up, right, and you have the hinge and you're looking at what the hinge can do, it's going to have some internal and some external power, right? So we'll just say the hinge X force and the hinge Y force. And in both of these, you're going to be able to, it's going to be able to hold and be able to support more than if there was no hinge, right? So the hinge creates more flexibility and it makes your span shorter, which is something else that's key. So definitely, if you got a continuous beam, it has an internal hinge. I mean, things that are happening within that internal hinge is the most important thing, because that is going to help with how your loads are able to be supported. So. See. All right, let's look at number 3. All right, what defines statically indeterminate structures in structural analysis? Given, what information are we given here? So we know that we're looking at some statically indeterminate structure, all right? And we're trying to find the definition. Cool. I'm trying to find the definition of statically indeterminate. I'm going to search statically indeterminate and see something comes up. Elementary statically determinate structures, the force. The force method is typically used to solve for elements or structures with a single degree of indeterminacy. Okay. Deflection resulting from the removal of a redundant support is equal. Okay. So I don't know if I don't think I need that. Statically indeterminate here. So they have unstable equilibrium. No. If you're typically if you're statically determinate or indeterminate, you are stable. So because here are the 3 different classifications that it can be. It can either be unstable, stable, and statically determinate, or stable and statically indeterminate. And we're looking at statically indeterminate. All right. All right. B, they have excessive support reactions. I don't, it's kind of hard to define excessive support reactions. So it doesn't really make sense to me. They have more unknown forces or reactions than the equations of equilibrium can solve. So they have a lot, there's more unknowns. There's more unknown forces than known forces. And I can see that. So yes, C. And what about D? They have fewer unknowns. So what this really means is basically it has more, right, unknown forces or reactions. So this is greater than reactions plus members are greater than the amount of joints, right? So if it was stable and statically determinate, you would have reactions and your members are equal to the amount of joints. So you typically, I think, know the joints, but you don't know like the some of the reactions that are in place, and so that's why it makes it statically indeterminate. But what they're saying is they have fewer unknowns. So that means that it would be unstable, right? But it's not the case. So C would be our answer. All right. So this concludes the elementary statically indeterminate structures. Kind of some conceptual stuff there. In the next video, we're going to be looking more at loads, load combinations, and load paths. So I will see you in the next video.